The space race has taken a nuclear turn. Superpowers are preparing to plant reactors rather than flags on lunar soil. The US now fast-tracking plans to build atomic infrastructure on the moon.
When Michio Kaku stepped onto the stage for his latest talk, the anticipation in the room felt almost electric. The celebrated theoretical physicist, known for his deep explorations into the mysteries of the cosmos, wasted no time before dropping a statement that instantly pulled the air from the room. The moon, as we have long understood it, might not be what we think it is. This wasn't a mere poetic musing or a speculative aside. It was presented with the confidence of someone standing on the edge of a significant scientific shift. For decades, the moon has been portrayed in textbooks and documentaries as a lifeless satellite, the product of cosmic happenstance, orbiting our planet in an eternal celestial dance. Yet here was Kaku, suggesting that the very assumptions at the foundation of that narrative could be wrong. Before we start, smash the like and subscribe buttons for more updates. He began by tracing the conventional story, the widely accepted giant impact hypothesis, where a Mars-sized body collided with Earth billions of years ago, ejecting material into space that eventually coalesced into the moon. While the theory has been compelling, matching much of the observed data, Kaku pointed out that new measurements, deep space observations, and seismic readings from past lunar missions have started revealing inconsistencies too significant to ignore. The moon's density, its unexpected distribution of certain isotopes, and the strangely precise nature of its orbit were just the beginning of the anomalies. These clues, he argued, have long been overlooked or downplayed because they did not fit neatly into established frameworks. The moon's mass is oddly light for its size, possessing a lower density than expected. This alone wouldn't be enough to raise suspicions, but combined with its peculiar mineral composition, the riddle deepens. Samples returned from the Apollo missions showed isotopic ratios eerily similar to those on Earth, far more so than one might expect if the moon had formed from a completely separate planetary body. While the giant impact hypothesis accounts for some of this similarity, the exact match in certain oxygen isotopes remains puzzling. It is almost as if the Earth and Moon were forged from the exact same batch of cosmic material under conditions more controlled than mere random chance would allow. He then shifted the focus toward structural and seismic data, revisiting the surprising results from instruments left on the Moon decades ago. Some of these experiments, designed to measure lunar quakes, suggested the Moon rang like a bell when struck by meteor impacts, or when stages of spacecraft were deliberately crashed onto its surface. This ringing phenomenon hinted at a highly unusual internal structure, one that defies simple models of a homogeneous rock sphere. While this ringing does not literally mean the moon is hollow, it raises profound questions about what lies beneath its surface. Kaku noted that certain layers within the moon are unexpectedly uniform in thickness, almost engineered in appearance, and that such precision in a natural satellite is extremely rare. Another remarkable point he brought forward involved the moon's orbit. The moon's distance from Earth, its perfect angular size relative to the sun during eclipses, and its locked rotation, always showing us the same face, have long fascinated astronomers and casual observers alike. While these features can be explained through tidal locking and orbital mechanics, Kaku emphasized the improbability of the combination of factors aligning so perfectly. This, he argued, might be a coincidence of cosmic proportions or an indicator that the moon's history is far stranger than we've dared to imagine. He wove in the significance of newly gathered data from recent lunar probes, which have detected unusual concentrations of certain metals beneath the surface, some of which do not occur naturally in abundance on most planetary crusts. These metals were found in regions deep enough that they could not have simply been deposited by meteorite impacts. Coupled with radar observations revealing void-like cavities beneath the crust, the findings hinted at processes or events in the moon's formation that are not accounted for by current models. Kaku then touched upon ancient records and myths, not as evidence in themselves, but as cultural artifacts worth noting. Across civilizations, from Sumerian texts to Native American legends, there exist stories that speak of a time before the moon hung in the sky. While such tales are often dismissed as metaphor or allegory, the sheer recurrence of the motif intrigued him. He did not claim these myths proved anything, but their consistency across continents suggested that humanity's relationship with the moon might have a longer and stranger history than we currently acknowledge. From here, the discussion took on an almost cinematic quality as Kaku described the potential scenarios that could explain these mysteries. One possibility involved a far more complex early history of the Earth-Moon system, with multiple large impacts and rearrangements of planetary material over time. Another possibility entertained was that the Moon's creation was influenced by forces or events we have yet to understand, perhaps phenomena that challenge the limits of known physics. He even hinted that, in the most extreme interpretations, some scientists have toyed with the notion of the Moon being in some capacity artificially altered in deep time, not by any known civilization, but perhaps by processes or intelligences beyond current human comprehension. The implications of such revelations are vast. If the Moon's formation does not fit neatly into naturalistic explanations as we understand them, it could mean our models of planetary formation are incomplete or fundamentally flawed. It could also shift how we interpret the history of the early solar system, possibly revealing a hidden chapter involving cosmic-scale events that shape not only our planet but the conditions for life itself. The Moon's role in stabilizing Earth's tilt, influencing tides, and potentially nurturing life would make any new understanding of its nature all the more significant. Kaku spoke at length about how technology now allows us to probe deeper into these mysteries than ever before. High-resolution lunar mapping, gravitational field analysis, and advanced spectroscopy are giving scientists unprecedented insights into the Moon's geology and structure. Each new piece of data is like a brushstroke on a much larger, more intricate canvas, one that might depict a Moon with a far more enigmatic identity. He underscored that these scientific puzzles are not just academic curiosities. The Moon is central to humanity's future in space. Plans for lunar bases, resource extraction, and using the Moon as a launch point for deeper exploration all depend on understanding its nature. If its internal composition or history holds unexpected surprises, these ventures could be affected in ways both challenging and advantageous. For instance, if certain rare metals exist in abundance beneath the surface, they could revolutionize space industry. Conversely, if its structure is more complex and unstable than we think, that could pose engineering and safety challenges for future colonization. Throughout his talk, Kaku maintained a balance between grounded scientific reasoning and an openness to possibilities. He made it clear that while some ideas might sound extraordinary, they stem from tangible anomalies in the data. Science, he reminded his audience, progresses not by ignoring inconvenient facts, but by confronting them head-on. It is in those mismatches between theory and observation that breakthroughs are often born. He described ongoing missions by various space agencies that aim to drill deeper into the lunar crust, map its gravitational anomalies in finer detail, and search for clues buried in shadowed craters untouched by sunlight for billions of years. These dark craters, he explained, act as cosmic freezers, preserving materials from the earliest epochs of the solar system. If the Moon indeed harbors secrets about its origin, these frozen vaults might be the key to unlocking them. Kaku also pointed to the Moon's influence on human imagination as an indicator of its profound significance. For as long as humans have gazed upward, the Moon has been a beacon, guiding sailors, inspiring poets, marking calendars, and shaping mythologies. To suddenly realize that the object which has served as our celestial companion for millennia might be far stranger than we thought is both unsettling and exhilarating. It challenges not only our scientific understanding, but also our cultural and psychological relationship with the night sky. The discussion inevitably stirred a mix of wonder and unease. Wonder, because the idea that there is still so much to learn about something so close to us rekindles a childlike curiosity about the universe. Unease, because it forces a reevaluation of our place in that universe. If the Moon's history is different from what we have assumed, then perhaps Earth's history is too. It might mean that we are participants in a cosmic story, more intricate and less random than we have ever imagined. He delved into the concept of cosmic coincidences, questioning whether phenomena like the Moon's size and distance relative to Earth and the Sun could truly be random. The perfect fit of the Moon over the Sun during a total solar eclipse is one of those coincidences that seems almost too perfect. In the strict language of science, coincidences do occur, but when they pile up in ways that influence planetary stability, climate, and the potential for life, they deserve closer scrutiny. Could the moon's presence be part of a delicate balancing act that made life on Earth possible? If so, what does that imply about how common or rare such circumstances are elsewhere in the cosmos? By the time Kaku wrapped up his talk, the sense in the room was that the moon, so familiar and ever-present, had become mysterious again. His revelations did not provide final answers, but instead widened the scope of questions. In science, that widening is a mark of progress. It means we have pushed beyond the comfortable boundaries of what we thought we knew, and are now standing at the threshold of new discovery. The moon, in his framing, is not a static relic of the past, but an active participant in an unfolding cosmic drama. Its true story might involve violent ancient collisions, hidden internal structures, exotic materials, and orbital characteristics that still defy full explanation. Understanding that story could reshape our models of planetary science, alter our strategies for space exploration, and even shift our philosophical perspective on humanity's place in the universe. What made Kaku's revelation so compelling was not just the data, but the way he conveyed the importance of looking beyond the surface, literally and figuratively. The moon's face, unchanging from our vantage point, hides a far side that we can only glimpse with the help of spacecraft. Likewise, its familiar glow hides a depth of history we have only begun to probe. Every new mission, every new sensor, every new analysis adds a layer of complexity to our picture of this ancient companion. As the audience left the event, there was a shared awareness that the moon might no longer be taken for granted. It is not just a backdrop for human history, but potentially a key to unlocking some of the deepest mysteries of our existence. If the anomalies Kaku discussed continue to hold up under further investigation, they could prompt one of the most significant paradigm shifts in our understanding of the solar system since the advent of modern astronomy. The next chapter of lunar exploration promises not just technical achievements, but also a profound reshaping of our cosmic narrative. The moon, as Michio Kaku revealed, may be a far more complex and enigmatic entity than the cold, barren rock we once thought it to be. And in that realization lies both the challenge and the thrill of scientific discovery, an invitation to step beyond certainty and into the unknown, where the universe keeps its most compelling secrets. When Michio Kaku's remarks began rippling beyond the conference hall, the scientific community and curious minds alike found themselves grappling with the depth of his claims. What struck many was the way he connected obscure technical data with broader questions about the universe's design, forcing people to think about the moon not just as a physical object, but as a key node in a much larger web of cosmic relationships. One of the most striking extensions of his argument came when he addressed the interplay between the moon and the Earth's biosphere in ways that have been underappreciated. Most are aware that the moon drives the tides, but Kaku dug deeper into the idea that these tides may have played a decisive role in the emergence of complex life. The constant rhythm of tidal movements could have created environmental niches where life could gradually adapt from the ocean to the land. Intertidal zones, with their constant cycles of flooding and draining, provide a natural laboratory for biological experimentation. If the moon's properties were even slightly different, its mass, distance, or orbital eccentricity, the magnitude and timing of tides would change drastically. In this light, anomalies in the moon's formation become more than academic. They may have shaped the very trajectory of life on Earth. Kaku went further, explaining how the moon's gravitational influence has been quietly protecting Earth for billions of years. Its stabilizing effect on Earth's axial tilt prevents extreme climate swings. Without it, the tilt might vary wildly over relatively short geological timescales, creating environmental chaos that would make the evolution of stable, advanced ecosystems far less likely. This alone would be enough to justify a closer examination of how the moon ended up in its exact position and with its particular properties. If this stability is the result of an extraordinary set of coincidences, then we must consider the possibility that such conditions are exceedingly rare across the galaxy. The conversation naturally turned toward the methods scientists might use to probe the moon's mysteries in the coming decades. Kaku highlighted upcoming missions that aim not just to orbit or land on the moon, but to explore its interior with new levels of precision. Advanced seismic arrays, capable of detecting even the faintest tremors, could reveal hidden structures beneath the crust. Ground-penetrating radar deployed by autonomous rovers might map subsurface layers in 3 dimensions, exposing cavities, mineral deposits, or geological formations inconsistent with current theories. These tools, paired with deep drilling rigs capable of reaching previously inaccessible strata, promise to provide the kind of data that can settle long-standing debates or spark entirely new ones. But Kaku did not stop at technological hardware. He pointed to the emerging role of artificial intelligence in space exploration, noting how AI can sift through colossal data sets from lunar missions far more efficiently than human analysts. Machine learning algorithms could spot subtle correlations in mineral distributions or gravitational anomalies that would escape the human eye. In some cases, AI might even propose new hypotheses for the moon's origin based purely on statistical patterns in the data. This blending of human curiosity and machine precision, he suggested, could be the key to breaking through decades of scientific stalemate. Perhaps one of the most tantalizing elements of Kaku's discussion was his speculation about what might lie in the moon's permanently shadowed craters. These regions, never touched by sunlight, maintain temperatures so cold that they preserve volatile compounds in a pristine state. Hydrogen, helium, and other elements trapped there could tell the story of ancient solar wind patterns. More intriguingly, some scientists suspect these craters may hold cometary ice billions of years old, material that predates the formation of the Earth itself. Analyzing such samples could offer direct insights into the chemistry of the early solar system and, by extension, the possible origins of life across the cosmos. The moon's far side occupied another significant portion of his narrative. Long hidden from Earth by tidal locking, this hemisphere has already surprised scientists with its thicker crust and abundance of certain rare minerals compared to the near side. The far side's massive South Pole Aitken Basin, one of the largest known impact craters in the solar system, could be a window into the moon's deep interior. Kaku described how drilling or robotic excavation in this region might uncover materials from the mantle, perhaps even revealing unexpected layers or compositions that challenge the standard model of lunar formation. From there, Kaku explored the possibility that the moon story is inextricably linked to that of the early Earth in ways we have yet to fathom. If the two bodies share such remarkable isotopic similarities, it may mean that the processes that shape them were more intertwined than previously thought. One scenario he entertained involved the Earth and Moon forming side by side from the same circumplanetary disk, with subsequent events subtly modifying their orbits and compositions. Another possibility is that multiple proto-moons may have existed in Earth's orbit before coalescing into the single body we see today. These scenarios, while unconventional, are not without precedent elsewhere in the solar system, where complex satellite systems orbit giant planets. The audience was particularly attentive when Kaku shifted to a broader astrophysical perspective. If the moon truly is unusual in its size relative to Earth, its orbit, and its isotopic match, then it may represent a rare category of planet-moon systems. Astronomers searching for life-supporting exoplanets might need to consider the presence of large moons as a critical factor in habitability. This would fundamentally change how exoplanet surveys are designed, encouraging a focus not only on planets in the habitable zone, but also on their potential lunar companions. The potential implications for human space exploration were equally compelling. Kaku envisioned a future in which lunar bases serve as both scientific outposts and staging grounds for missions to Mars and beyond. However, if the moon's composition, internal structure, or history turns out to be stranger than anticipated, it could influence the choice of base locations, the engineering of habitats, and the strategies for resource extraction. For instance, if certain deep-layer metals are more abundant than expected, mining operations could become a central driver of lunar colonization. Conversely, if structural anomalies pose geotechnical hazards, entire regions might be deemed unsuitable for long-term human presence. The discussion also ventured into the realm of planetary defense. The moon has acted as a partial shield for Earth, absorbing countless impacts over billions of years. Studying its crater patterns and distribution could improve our understanding of asteroid and cometary threats, refining models of how often such objects cross Earth's path. This is not merely a matter of historical curiosity. It has direct implications for predicting and preventing catastrophic impacts in the future. Kaku's remarks inspired new lines of thought about how the moon might serve as a record of events long erased from Earth's geological memory. Our planet's active tectonics and weather have obliterated much of its ancient history, but the moon, geologically dormant and lacking an atmosphere, preserves an almost unbroken record of the solar system's violent past. Layers of dust and rock on its surface could hold the signatures of supernovae, gamma-ray bursts, and other cosmic events that influence the trajectory of life on Earth. Extracting and decoding that record might be akin to reading a cosmic diary spanning billions of years. The role of the moon in human consciousness also emerged as a theme, not as romanticism, but as an anthropological reality. Civilizations throughout history have embedded lunar cycles into their calendars, rituals, and navigation systems. Kaku suggested that our evolutionary psychology may even be attuned to the moon's presence, its phases, its light in the night sky, and its predictable rhythms. If the moon's origin story changes, it subtly alters our own story, challenging the deep-seated cultural and psychological frameworks that have been shaped under its constant gaze. In the midst of these grand reflections, Kaku did not shy away from technical puzzles still awaiting solutions. One example he raised was the distribution of mass within the moon, its mascons or mass concentrations beneath large impact basins. These dense regions discovered during the early lunar missions significantly affect spacecraft orbits. Understanding their nature is essential not only for scientific purposes, but also for the practicalities of long-term lunar operations. Why these mascons are so precisely located and how they formed remain open questions, and resolving them could be pivotal in deciphering the moon's deeper history. He also drew attention to the subtle but measurable recession of the moon from Earth, about 3.8 centimeters per year. While this drift is well understood as a product of tidal interactions, projecting it backward through time leads to scenarios that complicate our understanding of the moon's early orbit. If the moon had once been much closer, the tidal effects would have been extreme, possibly too disruptive for early life. Reconciling these dynamics with the evidence for life's relatively early emergence on Earth adds yet another layer to the puzzle. Then there was the matter of the lunar magnetic field. The moon today has only weak traces of magnetism, but certain rocks brought back by Apollo astronauts show evidence of having been magnetized in the past by a much stronger global magnetic field. The existence of such a field implies that the moon once had a molten convecting core, something difficult to square with its small size and rapid cooling rate. If the moon's core behaved differently from what physics would predict, that anomaly could be a vital clue to its unique origin. Kaku's talk also ventured into the chemistry of the lunar regolith, the fine dust that covers its surface. Recent analyses have found water molecules bound within the regolith grains as well as hydroxyl groups in quantities far greater than expected for an airless body constantly bombarded by solar radiation. The source of this water remains uncertain. While some of it may come from cometary impacts, other mechanisms, perhaps involving solar-wind interactions with oxygen in the soil, might be at play. Understanding these processes could illuminate not just the moon's history, but also the chemistry of airless bodies throughout the solar system. He emphasized that the next generation of lunar explorers will not be content to plant flags and take samples. They will be conducting experiments on site, in real time, with equipment capable of high-precision measurements never before attempted on the moon. This shift toward a laboratory-based presence could accelerate discoveries, allowing scientists to adapt their questions and methods on the fly as unexpected findings emerge. Kaku's ability to weave together the practical, the speculative, and the philosophical created a tapestry in which the moon became more than an astronomical object. It became a mystery at the heart of our planetary system, a puzzle whose solution might reverberate far beyond lunar science. The stakes, he suggested, are nothing less than our understanding of how planets, moons, and perhaps life itself come to be. By the close of his presentation, the sense of urgency was palpable. The moon is not simply waiting for us to uncover its secrets. It is a dynamic partner in our journey toward cosmic understanding. Every year that passes without deeper investigation is a year in which clues could be lost to the relentless impact of micrometeorites or altered by the slow march of geological processes. If the moon's story is as extraordinary as the anomalies suggest, then the time to uncover it is now. It was this fusion of scientific rigor and visionary scope that made Kaku's revelation so electrifying. He had not merely presented data, he had reframed the moon itself as a frontier both ancient and new, both familiar and alien. For those who heard him speak, the moon will never again be just the pale light in the night sky. It will be a question mark, a challenge, and an invitation. After the initial shock of Michio Kaku's claims began to settle, the discussion expanded into even more unconventional territory. He posed a series of questions that pushed the limits of planetary science. What if the moon's deeper layers contained materials unknown to Earth's geology? Not just rare metals or exotic crystal formations, but compounds forged in conditions no longer present in our solar system. Such materials could be remnants from the earliest stages of planetary formation, preserved in the moon's inert environment long after Earth's dynamic crust recycled and erased them. Kaku explained that spectroscopic readings from orbiting satellites have already hinted at chemical signatures not fully accounted for in our current models. Some wavelengths of reflected light from certain craters indicate the presence of highly reflective minerals that, on Earth, tend to form only under extreme pressure and temperature conditions deep within planetary mantles. If confirmed, this would imply that vast sections of the moon's interior were once subject to forces far greater than its modest size would suggest. It raises the possibility that the moon has undergone processes more akin to those inside much larger celestial bodies. From this point, his vision shifted toward the engineering marvels that might be necessary to explore such depths. Drilling through the lunar crust is not simply a matter of scaling up Earth-based equipment. The moon's low gravity, lack of atmosphere, and abrasive dust present unique challenges that require innovative solutions. Kaku described experimental concepts for robotic burrowing machines equipped with self-repairing joints and dust-repelling coatings, capable of tunneling kilometers beneath the surface without human intervention. The data gathered by such machines could transform our understanding of the moon's internal layering, potentially revealing anomalies that cannot be seen from above. The subject of ancient impacts arose again, but this time Kaku emphasized their potential as investigative tools. Every large crater on the moon is essentially a drill hole blasted open by a meteorite, exposing subsurface materials. By studying the debris fields and central peaks of these craters with precision instruments, scientists might gain direct access to the moon's deeper strata without drilling at all. Some of these impacts date back to the late heavy bombardment period, over 3.8 billion years ago, meaning they could contain unaltered records of the solar system's formative years. Perhaps most intriguingly, Kaku discussed how gravitational mapping has revealed subsurface structures beneath the moon's maria, its vast, dark plains, that defy simple geological explanation. These regions appear to overlay dense linear masses that stretch for hundreds of kilometers. While mainstream interpretations point to ancient lava flows or solidified magma channels, their geometric regularity stands out. If these formations prove to have patterns inconsistent with purely volcanic origins, they could point to geological processes we have never observed before, or to events that challenge the natural history narrative entirely. He also delved into the role of the moon in shaping Earth's atmosphere over geological time. While the stabilizing of the axial tilt is well known, Kaku speculated that the moon's gravitational influence might have moderated atmospheric circulation patterns, preventing prolonged periods of planetary instability. This could have implications for the early climate, possibly influencing when and how oceans formed permanent bodies of water rather than boiling away or freezing solid. Such long-term climate moderation would have provided a consistent backdrop for life to evolve, and its absence in other planetary systems might be a reason why Earth-like worlds are so hard to find. Another frontier he described was the potential to use the moon as a base for deep space astronomical observation. Without an atmosphere to distort light and with its far side shielded from Earth's radio chatter, the moon could host observatories of unprecedented sensitivity. If the moon's history turns out to be exceptional, these observatories could simultaneously study its surface and serve as listening posts for faint signals from the early universe, potentially linking lunar science with cosmology in a direct and profound way. Kaku also entertained the idea that the moon's gravitational influence extends beyond tides and axial stability into more subtle realms, such as influencing volcanic activity on Earth. While speculative, he noted that tidal stresses in Earth's crust could, over immense timescales, play a role in cycles of geological activity. If the moon's origin story changes, it could prompt a re-evaluation of the timelines and triggers of Earth's own volcanic and tectonic history. Looking further ahead, Kaku envisioned the moon as a testbed for experimental physics. Its vacuum environment, stable ground, and minimal seismic activity make it ideal for experiments in quantum mechanics, gravitational wave detection, and even long baseline particle accelerators. Understanding the moon's true structure would be critical in choosing optimal sites for such installations. If the crust hides unusual densities or magnetic anomalies, they could interfere, or perhaps assist in certain types of experiments, opening new frontiers in basic science. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Michio Kaku's moon theory? What do you expect happens? We want to hear from you. Thank you for watching and see you next time.